Welcome to a free body diagram review. If you've been absent or you just want a little extra review, you will appreciate this, I believe. I'll try to go quickly through it. We'll do separate videos per page. So starting on Unit 6, Newton's Laws, page 3 of the notes, how are forces drawn and calculated. Let's look at the first two examples. So generally speaking, they're talking about a box on a table and they're asking about forces. A free body diagram is your friend. So put the box on the table. They gave you the mass, 5 kilograms. So mass, 5 kilograms. Mass is not a vector. Don't draw it with an arrow. What can you draw, however? So here's a little cheat sheet of different forces we deal with. Force of gravity, aka weight. The normal force, friction, spring force. External pull forces, like tension from a rope. And then, of course, put them all together, you get the net force. In order, generally, the way I put the force is a good idea. Usually we have weight, and weight is pretty straightforward. Our weight vector will point straight down and do a little side work. Fg equals mg. Over here we have 5 kilograms times 9.81 meters per second squared, and that comes out to approximately 49 newtons. Okay, so we have a weight of 49 newtons. Now, before we move quickly to figure out anything else, let's see what forces are involved. Well, the box is at rest on a level table. It's not trying to move anywhere, no friction. No springs involved. They're not talking about a pull force externally, so no F external. Is there a normal force? Yes. However, though you probably already know its magnitude, don't be so quick to draw it. First, let's do what they explicitly tell us or imply with the question. If the box is at rest, you are in equilibrium. If you are in equilibrium, the net force is 0. If the net force is 0, then the normal force must balance the Fg. Otherwise, you would not have a net force of 0. Normal, 49 newtons, good to go. Next one, a 10 Newton crate pulled right. So here's a crate. It's a 10 Newton crate. That is not the mass, that is its weight, 10 newtons. So we can draw its weight, Fg, 10 newtons, good to go. Okay, it's pulled right by a force of 5 newtons. They're explicitly telling you there is a pull force, there is an external force. Here it is, we're going to draw it, 5 newton, you can label it F, you can label it F external, you can label it F APP for force applied, it doesn't really matter. There's a force pulling it to the right, 5 newtons, so we got that covered, good. They also tell us that the box is at rest. When you see it's at rest, that's equilibrium. Now we know the net force is 0 newtons, so the net is done. There's no spring, of course, and now we have the balancing forces remaining, the normal force and the friction force. Okay. Going back to last unit, we discussed the details of normal and friction, so let's just jump to applying them. This clearly is not an equilibrium or a net force 0 scenario. So what's missing? Well, in the perpendicular or vertical direction, Fg has to be balanced by something. The only something left is the normal force. So the normal force in this case will balance the Fg, 10 newtons. In the parallel or x direction, we need something to provide that net force 0, something to balance the external of 5 newtons. The only thing left is the frictional force. You cannot just put another F external in there. You put them if they tell you. If not, no. Friction must be the balancing force. Sometimes I like to draw it along the surface here because that's where it's acting. Force of friction will balance your 5 newtons. There it is, normal done, friction done. There's your complete picture. By the way, we didn't mention it, but because A equals F net over M, if the net force is 0, the acceleration is 0. Over here, if the net force is 0, the acceleration is 0. All right, moving on. Here, I don't like the wording of the statement, so instead I'll give you the diagram because often you get a diagram of this sort and then you make sense of the diagram. So what I've tried to tell you here is that this thing is being pulled from each side, force external, 15 newtons, as it says here, and this side. By the way, it does not matter exactly where you locate your vector. Vectors can be translated freely. So if you want to put this arrowhead, oh, they're moving together. But if you wanted to put this arrow on this side, and draw it this way, and this arrow on this side, and draw it this way, that would be perfectly fine. In fact, for all of these that we've done, for example here, they're telling us a 10 Newton box again, that's its weight, so I'll draw an FG of 10 Newtons. This arrow can also equally be drawn up here. It's pointing down and it has a 10 Newton magnitude, that's all it needs to tell you. So I personally like to put them here, start in the center and work out. You can start out and work toward the center, it makes no difference, you get the same results. Okay, this all looks nice. Let's see what else we have here. It's being pulled, it says it's frictionless, so no friction. We did FG, we did the external forces. There's no spring, as often there will not be. And so it's being pulled horizontally, force from each side. Okay, frictionless. So this is it now. In the horizontal direction we have everything. In the vertical direction, well, what else is there? There's the normal force. And the normal force, remember, is a balancing force. It balances whatever needs to be balanced in the vertical direction or the perpendicular to the ground direction. Here, the only thing that needs balancing is the weight, so the normal force, too, is 10 newtons. From this, we can come up with the net force. They didn't tell us constant velocity. They didn't tell us at rest. They gave us all the forces. Balance in the x, balance in the y. F net is 0 newtons. Acceleration is 0 meters per second squared. So that's covered too. We just did the normal. One thing that says it's being pulled horizontally to the left. Forces go on this diagram. Net force goes as the summary up above. But don't put a velocity arrow in there. If you want, you can put a little something down here. Its velocity is to the left. And you may say, wait a minute. How is that possible? How is it that we're pulling left and pulling right the same amount, yet it's moving left? Well, actually, that's perfectly possible. That's fine. In fact, often that's how it is. If you instead go and look at a car on the highway. Here's the highway. Here's your little buggy driving along. If you are driving at a constant velocity of, let's say, 55 miles per hour in this direction, what does your force diagram look like? Well, your car has weight. There is normal force from the ground if you're on a level stretch of the road that's nice, easy, equal to the weight. You have a force forward. You might want to call that force of like your engine. Really, it's the road is pushing your car forward, but let's not worry too much about that. So say, call it force engine for short. And is there anything backward? Well, yes. In fact, if you take your foot off the gas, you experience it. There is a frictional force both from the air and the road. So even while you drive cruise control 55 miles per hour on the highway, you are living this example. We've said it, constant velocity or at rest are both examples of equilibrium. You could be in equilibrium and moving. Now you actually have to believe it. All right, pause. We'll go to the next video if you need the next page.